In the past two videos, I've given a very brief overview of the characteristic X-ray spectrum. In this and the next video, I shall go into more detail to get a better understanding. So let me say a little bit about the kind of typical wavelengths and energies of the X-ray photon. Now, the wavelengths of X-ray is typically between about 0.1 nanometer to 10 nanometers. The corresponding frequency of the photons, lambda and f are related by f equals to speed of light over lambda. Right, so if you know lambda, you can find f, and you know f, you can find photon energy, hf. So if you do that, you find that for 10 nanometer wavelength, that corresponds to photon energy of just over 100 eV. Actually, it's 124 eV, but I just say about 100 eV. And this 0.01 nanometer wavelength would correspond to about 100 keV. So these are the kinds of wavelengths and photon energies that we are looking at. Okay, which is why even if just by looking at this, right, if you want to produce a photon using an electron beam hitting a metal target, if you want to produce a photon with this kind of energy range, you have to use a voltage with that kind of range as well. So if you want to produce a photon with 100 keV energy, you must use a voltage to accelerate the electron beam up to 100 kilovolts. Then the electron will gain this amount of kinetic energy which can produce such a photon through the breaking effect when it hits the metal target. And just to get a bit more familiar with X-ray, actually I think nowadays most of us have some familiarity with X-rays. Many of us would have gone through some X-ray of our body at some stage of our life. So let me just you might have heard of terms like soft X-ray and hard X-ray. So let me just give an example of the kind of range of values. Now, a soft X-ray has photon energies in the range of about 100 to 10 keV, and it is often used. This range of photon energy, soft X-ray, they cannot really penetrate the body completely. Okay, so it is actually not used for normal X-ray photos of, say, our skeleton, for example, but it is used for imaging softer tissues, like in mammography. To detect breast cancer in women. Now, you might also have heard of hard X-ray. The hard X-ray corresponds to photons with higher energies. Say from about 10 keV to about 100 keV, and these are used in normal X-ray imaging of our body and skeletons, radiography as it is called, and also in airport security, right, to X-ray our luggage. So that's that. And okay, so that gives us an idea of where we are at in the electromagnetic spectrum. So coming back to the example of molybdenum. Now I've talked about how when you have this beam of electrons hitting, say, a molybdenum metal, X-ray would be produced. X-ray. Now let me draw a typical spectrum for molybdenum. Right, I'm going to assume an energy of 100 keV of the electron. Now, as I have sketched previously, let me sketch this again. The graph for the X-ray spectrum. I'm going to sketch it as a graph rather than as a visible light spectrum, which is often used for hydrogen spectrum. So as I've described previously, there will be a continuous background due to the breaking effect of the electrons, and there would be a few peaks. Due to the transitions. And this minimum wavelength corresponds to the maximum K. So let me now try and calculate this minimum wavelength. Just get a better understanding of this. Right. So we're saying that the minimum wavelength corresponds to the case where all of the electrons' kinetic energy is converted to a proton. Okay. Because in general, doesn't have to be all, it can be like half of it or some fraction of it converted to the X-ray photon. That's why we have this continuous spectrum here. So, but if the whole lot is converted, let's see how we can find it. It means that the energy of that photon would be this full kinetic energy, which is 100 keV. So 100 times 10 to the power 3 for the K, and times 1.6 times 10 to the minus 19 coulombs for the E. Okay, and the answer would be in joules. So since HF is the photon energy, that will be equal to this value, and since F lambda is equal to the speed of light, we can find the corresponding minimum wavelength. Okay, so that would be c, speed of light over frequency, and frequency would be e over h. So over frequency would become c times h over e. Okay, from there, and putting in the numbers, let's see what numbers we need. Let me write it down here. Speed of light 2.998 times 10 to the power of 8 meters per second, and we need the Planck's constant, which is 6.63 times 10 to the power of minus 34 joule second. Okay, so putting in the numbers for this, we would find using our calculator 0.01240 nanometer, and that would be our minimum wavelength. That would be this. So that would be this wavelength here, where the continuous background comes to an abrupt stop, would be 0.01240 nanometers. Okay, and in the case of the molybdenum X-ray spectrum, it has been measured a lot. I think you can even search for this on the internet. Just search for characteristic X-ray spectrum of molybdenum, and you would actually find pictures like that, and with numbers for the wavelengths or the photon energies. Now I'm just going to write down what I found. This biggest peak, which is called K alpha, has a wavelength of 0.0707 nanometer. Okay, and then the others have other wavelengths. But it is this number that I'm most interested in for this and the next video, so I'm just going to write that one down. Okay. So as I have mentioned in the last video, the K alpha spectrum is due to transitions is due to transition from from the second orbit to the first orbit. Now, how do we actually know this? Well, it's a little bit complicated. I'll come back to this question of how we know it is a transition from second to first orbits. Let me draw a picture of that so that we know what we are trying to do. So this is right. Let's say this is the proton. No, the nucleus of metal. Doesn't have to be a metal, just the nucleus of an atom of any elements. Suppose that there are a number of protons here. Suppose that there are Z protons. So the charge will be Z times E. Okay, Z is a number which is often used to, is called the atomic number, and it's often used to represent the number of protons. Okay, and in the case of molybdenum, which is this one, I better write this down. This is for molybdenum metal. The chemical symbol is MO. So for MO, Z is 46. No, actually it's 42, I think. Okay, so right, so we have this Z number of E in the proton, so the total charge is plus ZE, and we know from Bohr's atom, remember for in the case of Bohr's model for the atom, I've only talked about hydrogen, the hydrogen case, where there's only one proton in the nucleus. In this case, for other elements, there can be many more protons in the nucleus, but the idea, Bohr's idea can still be used in this case, at least to some extent, if we just replace the charge at the center by the number of protons times E. So let's try that for the X-ray spectrum. So, and using Bohr's condition, Bohr's and de Broglie's condition, that there must be a whole number of wavelengths in around the orbits. We understand that only certain radii of orbits are allowed. Now in this case, I'm mainly interested in the K alpha line. I'm interested what I really like to do is to check whether a transition from this second level to first level would really give me this wavelength. Alright, because this is something that has been worked out over the years, and today we understand that this is the case. But in the very early days, in the 1910s or 20s, right, there is still a lot of people are still very unsure in the beginning about how this about what's actually going on, what produces this line, and we should really try and understand why and how we actually know that this transition would correspond to this peak. And the only way really is to calculate the energy, because when we calculate the energy we can find the same answer, then that shows that this picture is correct. Okay, so that's what I'm going to try and do now. Now, in order to find the energy change when an electron falls from this orbit to this orbit, we already know how to do that with the Bohr's atom. So it's just a matter of repeating the exercise. Okay. So in order to do this, I would first need a formula. Or it's easier to make a formula for the total energy of each orbit, the Ke plus the Pe. Okay, so let me start by writing down the expression for the centripetal force. So the centripetal force is mv squared over r, where r is the radius of the orbits, and that is the mv squared over r, that force there. So we know that this must be equal to 1 over 4 pi epsilon naught Z E, is the charge of this nucleus, times E, which is the charge of the electron, that divided by the radius squared. Okay, and following the steps that we have used for Bohr's model, just bring the r squared over to here, separate out the v, again, m v r is equal to, that would be z E squared over 4 pi epsilon naught. Okay, and this momentum times r, we know from Bohr's condition and from de Broglie's relation that it must be equal to the whole number times Planck's constant over 2 pi. So that's the V there. I have this ZE squared over 4 pi epsilon naught. Finally, I can rearrange this whole lot to give V is equal to Z E squared over 2, the pi and the pi cancel, epsilon naught, the NH comes down here. So that gives us the V. Okay, and with this V, we are ready to calculate the total energy. So therefore, total energy, total E is equal to the kinetic energy, which is half mv squared, plus the potential energy, which is minus 1 over 4 pi epsilon naught, charge of the nucleus times charge of the electron divided by r, minus because they are oppositely charged. Okay, so, and this is equal to, now from up here, if you look at this and compare this with this, you see that these two are the same, except that I have r squared here and r here. Now what I could do is I can multiply both sides of this by r. See, if I do that, that cancels and r squared becomes just r, and this would look exactly the same as this. And since we know that this is equal to mv squared, I can simplify this by replacing this by mv squared. So this is half mv squared minus mv squared. You see, it's looking quite simple now. Alright, so E is actually equal to minus half mv squared. So we have a very, very simple result. And we already know what V is. V is equal to that. So I can substitute that into the V here. Okay, and that gives me minus 1 over 2m times this thing squared. So ZE squared over 2 epsilon naught and h whole thing squared. And now we have a formula for E. Now this E is the E for the orbit number n, right? Orbit n, where n is 1 for this orbit, 2 for that orbit, and so on. So, since E is going to be different for different n, I'm going to add a subscript n here to remind myself that E depends on the n. Okay. And once we have this formula, we are ready to calculate the energy change when an electron falls from this orbit to this orbit. Because if you look at this, we know all the values here. We know m, mass of the electron, z, 42 if it's molybdenum, E, charge of the electron, we know, epsilon naught, permittivity, yes, h, Planck's constant, yes. So we know all this. And n would be 2 or 1. Okay, so we need to use n is equal to 2 and then use n equals to 1 to calculate the E1 and E2, to calculate the energies of the two orbits, and then we need to subtract them. And if we do that, we would get the photon energy emitted. Now, so for now, I'm not actually going to do this calculation, but I just want to mention one thing about this relation, which is that you see the En here depends on Z squared. depends on Z squared, the number of protons squared. Okay, and this relation is going to be very helpful in helping us in helping people to use this X-ray spectrum both for identifying elements and to understand what's going on when they do measurements. I'll talk about this in the next video.